Okay. We see that this will go away because B naught plus of course is anti-commute with C naught minus, so you'll get a delta naught B naught plus which is 0. Okay. And so we'll get a relation like delta naught C naught minus Q B tilde B naught plus is equal to 0. Okay, so all of these relations will make use of. Okay. And the reason that these relations are important is because eventually you have to analyze the properties of delta naught, right? And you have to show that delta naught, okay, will only contain physical state propagation, right? In general, delta naught is a matrix, okay, which contains both contributions from physical states as well as unphysical states, okay, ghost states for example. But you have to eventually show that only the physical states contribute. Okay, now let's say a few more words about how to represent delta f, okay, because you want to represent somehow delta f and delta naught as sum over states. Okay, so delta f, so if you recall, we had introduced this basis in the full Hilbert space. In full Hilbert space, we choose a basis chi r, okay, and independently chi r prime, okay, satisfying chi r prime chi s equal to delta r s. Okay, if you recall, you had introduced this in order to analyze the propagator. Okay, and then you have a completeness relation, okay, that chi r prime is identity in the full Hilbert space. Okay. So using this, we can write delta f as chi r prime delta f chi s prime. Okay, it's just a triviality. I just introduced two identity operators on two sides. Okay. But now let's recall how delta f is to be used. Okay. So we have delta f connecting two vortex, for example. Okay. Now at this vortex, okay, this is can be expressed in terms of some integral of a Riemann surface, okay, with various vortex operators inserted on the Riemann surface corresponding to all these external legs, and also the state chi r which is coming from delta f. Okay, that's the way this has to be evaluated. And similarly on this vortex, you have to insert chi s prime. Okay. But now recall that by ghost number conservation, okay, or not ghost number, by picture number conservation, okay, we must have only this state that is inserted here must be in H hat T, okay, because that's what conserves picture number. That's how you have chosen the picture numbers. And similarly here, so chi r must belong to H hat T, and similarly chi s prime must belong to H hat T. Is this clear? Okay, because unless if it carries any picture number other than those in H hat T, this will vanish by picture number conservation. Okay, so the only way you can get a non-zero contribution from this delta f is if the two sides have the right picture numbers. Okay, so even though we have written the delta f as it's an operator in the full Hilbert space, okay, the only part of delta f that really is relevant, okay, is when on this side there is a picture number -1 or -half, and similarly on this side there is a picture number -1 or -half. All picture numbers, yes. So this chi r is in general a basis states in all with a full Hilbert space, right? So then I can always write any operator then can be expanded like this. Okay, but now the point is that this chi r and chi s prime, okay, unless they are in picture number -half or -1, it doesn't contribute to the amplitude. So that's why we should restrict delta f. That's even though delta f as written here it doesn't say that it's only in the picture number -half or -1, but in actual application, you only have to restrict to that. That part is the relevant part, right? Rest doesn't matter. So which means when we talk about delta type, we can simply think of delta type projected in this subspace, right? That's where these are all in picture number -half or -1. Okay, rest of the terms you just ignore. So that's the way you should think of delta f, and the same is the case for delta naught. Well, the way I have written it here, the ones that are inserted on the amplitudes are chi r on this side and chi s prime on that side. See here both chi r and chi s prime, yeah, so this is chi s, you can write it as a bra, but we can always do BPC conjugation, that doesn't change the picture number. Well, see, H tilde was in picture number -3/2 and -1, right? This will be in H tilde and this will be in H tilde. Right? These are in H hat. See, I had introduced another set of bases where you had used phi r and phi rc, right? Where phi r was the basis states in H hat and the other one was in H tilde. Right? Here, I have just introduced two sets of basis states, each in the full Hilbert space. Right? Chi r is a basis state in the full Hilbert space. Chi r prime is also a basis state in the full Hilbert space. Right? The reason that I introduced two is because I want this orthonormality condition. Yeah. Yes. And all other picture numbers, exactly. That's right. Okay, so full Hilbert space means all picture numbers. Okay, and the point I'm trying to make is the relevant part of the picture number that we should pick up is the picture number -half or -1 on this side and on this side, the ones which are inserted on the amplitudes. Okay, so similarly delta naught that I can also write in this form. So delta naught should also be of the form chi r prime delta naught chi s prime, where chi r and chi s prime belong to H hat T. Because then chi r, chi s in general may not denote delta rs, because this inner product sometimes is antisymmetric, right? By Gauss number, the odd Gauss number sector, you cannot have a symmetric inner product, right? So it's just to keep track of the sign, right? If I could choose basis states where chi r, chi s is delta rs, I could have written just one set of basis states. Well, chi r c is chi r itself, because chi r in general spans the whole Hilbert space, right? So does chi r prime. So chi r prime is a chi r complement, right? But it's like with some extra signs added, right? Just to make sure that this identity holds for all RNAs. Right? In other words, sometimes if you want to choose the simplest set of bases, that you cannot choose chi r prime equal to chi r. Right? What you can do is that in the even Gauss number sector, we can choose chi r prime equal to chi r. In the odd Gauss number sector, we can choose chi r prime equal to minus chi r. Right? Then you can have a basis state like this. It's just because of this fact. Well, actually, it's a little more complicated, because the point is, if you take Gauss number 3, they are of course paired. But suppose you have chi s is a Gauss number 1 state, right? Its conjugate is a Gauss number 5 state, right? So it doesn't make sense to say that this is delta rs, right, if they are of the same kind, right? Whereas if you use chi r prime, that means if chi s is Gauss number 1, this should be Gauss number 5 and vice versa. Okay, but each can take all possible Gauss numbers. Okay? So it's just a technical point, it doesn't really matter at the end, because eventually what I'm going to get at is the following. Okay, so what I'm going to get at is that this means that we can write delta naught in the following way: as sum over A. Let me use the same notation I have used there. sum over A phi A psi A, where phi A is in H hat T and psi A is in H hat T. Okay. So what have I done? Okay, for example here, okay, I could take this to be the set phi A, and this whole thing, this is just after all a constant times chi s prime, I can declare as my psi A. Okay, you can always represent like this. Okay, but we want to be a little more efficient. Okay, this in general will give lots of states. Delta naught will be replaced by a linear combination of lots of states. Okay, but now we try to reduce the number of terms in this sum, okay, by requiring that phi a's are linearly independent and psi a's are linearly independent. Okay, so take phi a's to be linearly independent and independently psi a's to be okay. So this gives you the minimal set of terms. Okay, we are not demanding anything about what these are in terms of the original basis states. They can be anything. Okay, so what is the idea? Okay, that imagine that we write it in this form. Okay, maybe the arbitrary as a sum of all possible basis states. Okay, and then we find that not all the phi a's that are appearing here are linearly independent. Okay, suppose phi 1 is equal to phi 2 plus phi 3. Okay, then what we will do is that every term where there is a phi 1, I write it as phi 2 plus phi 3. Okay, so then there will be no term here which has phi 1. Is that clear? Right, I can always see, you think of these as coefficients. Okay, here just think of these as coefficients. Okay, and these as some basis states. Okay, we don't care that these are actually kits, just think of them as some coefficients, abstract coefficients. These are the basis states. Now, if these are not linearly independent, okay, we can always express this in terms of a linearly independent set of states. Okay, so if phi 1 is phi 2 plus phi 3, okay, you will write this as phi 1, phi 2 plus phi 3. Let's suppose that you have only 3 states, okay, times psi 1 plus phi 2 psi 2 plus phi 3 psi 3. Okay, and this now we can organize slightly better. Phi 2 times psi 1 plus psi 2 plus phi 3 times psi 1 plus psi 3. Okay, so if you had phi 1 psi 1, suppose the sum run from 1 to 3. Okay, phi 1 psi 1 plus phi 2 psi 2 plus phi 3 psi 3, and suppose phi 1 phi 2 phi 3 are not linearly independent, there is a relation of this form. Just rewrite phi 1 in terms of phi 2 plus phi 3. Okay, psi 1 remains as it is, then it's phi 2 psi 2 phi 3 psi 3, and you see that what you have done is that you have written it as in terms of phi 2 times something and phi 3 times something. So you have reduced the number of terms, and this you can declare as your new psi 1, let's call this, or psi 2 tilde, and this you can call psi 3 tilde. Okay. So if the phi a's are not linearly independent, you can reduce the number of terms by simply expressing the ones which are not linearly independent in terms of the others. Okay. The same you can do for size. Okay, given any representation, if you find that the sum of the size are not linearly independent, you can express the one that is linearly dependent in terms of the others, and you can again reduce the number of terms. Okay. So you keep doing it till you have the minimal set of terms. Okay. Because in the minimal set of terms, it must be that phi's are linearly independent and psi's are linearly independent. Right? Because if they are not, you can reduce the number of terms even further. Is that point clear? Okay, this you can do for any matrix. Okay, and hence you can do it for this. Now the reason that I am going through this is because this representation will be useful, because you see these phi's and psi's are eventually directly the states that are going to be inserted into the amplitudes. Okay, once you have written delta naught as phi a psi a, right, these are the ones which will be inserted on the two sides into the amplitudes, right? Because once you have a cut propagator, right, one side has state phi a inserted into the left amplitude, and other side has psi a inserted into the right amplitude. Okay, so you have to now study the properties of phi and psi, right? That's the goal. Okay, and you have to, if you can show that phi's and psi's are only physical states, then you are done, right? Because that means that in the propagator only the physical states propagate. Okay, are there questions? Now one point I want to mention here, even though I will not use it, is that typically the number of terms that arise in a sum like this will be finite. Okay, even though you start with the full string field theory propagator which has infinite dimensional Hilbert space, the number of terms that will appear inside delta naught is finite. Okay, and intuitively the reason is simple. Delta naught is a residue at the pole, okay, at certain value of k square. Okay. And we know that in string theory, okay, even though string theory has infinite number of states, at any mass level there are only a finite number of states. Okay, and this capital M is a renormalized mass, but nevertheless it's close to what the original masses were, right? Because if we are doing perturbation theory, so at any mass level there should be only a finite number of states. Okay, and hence we expect that the rank of delta 0 will be finite. Okay, and that rank of delta 0 is precisely the number of terms that appear in a sum like this. Okay, so you expect this to be finite, but finite in number, but this is not something that we are going to use. Okay, so now what you are going to do is to use these relations that you have derived for delta 0, okay, to restrict the form of phi and psi. So we start with b0 plus delta 0 equal to 0. Okay. This means that b0 plus phi a equal to 0. Okay. Why? Because psi a's are linearly independent. Okay, so if b0 plus delta 0 is 0, then b0 plus phi a times psi a is 0. But if psi a's are linearly independent, then it must be true for every a. Okay, that's the logic. Similarly, delta 0 b0 plus equal to 0 implies that psi a b0 plus equal to 0. Oh, I should have, oh, that I have already said. Phi and psi belong to H hat. Okay. Then we have b0 plus qb hat delta 0 c0 minus equal to 0. Okay. And this implies that b0 plus qb hat psi a equal to 0. Similarly, well, if this C0 minus you can just kill by applying a B0 minus on the right hand side. Okay, so you don't have to worry about the fact that there is a C0 phi a C0 minus. Similarly, delta 0 C0 minus QB tilde B0 plus equal to 0. Okay, and this implies that psi a C0 minus QB tilde B0 plus equal to 0. Okay. Now you can apply a B0 minus from this side and use the fact that QB tilde, conjugate of QB tilde is QB hat. Okay. To rewrite this equation as B0 plus QB hat psi A times B0 plus, sorry, I have already written B0 plus is equal to 0. Okay, so here I am using the fact that the way QB tilde and QB hat differ is that one has kg, the other one has gk, right? So when you try to take it on psi A, okay, by thinking of this as acting on the left rather than acting on the right, okay, the order of g and k will get reversed and QB tilde will get converted to QB hat. Similarly, B0 plus will come at the end, right? Because first we'll act this and then B0 plus. Okay, so this is what you get there. Yeah, so okay, just 1 minute, let me write, this is a phi A, this is not psi. Yeah, so C0 minus you can kill by applying a B0 minus. Because if you apply a B0 minus, then B0 minus kills this, right? So if you had a you had a C0 minus equal to 0, right? Now apply by a B0 minus kills this anyway, right? So only the anti-commutator will be picked up, so that removes the C0 minus. So basically having a C0 minus doesn't give any extra information because this is, since this is in H tilde T or H hat T, okay, because this is in H hat T, it's annihilated by B0 minus, right? So whether you put a C0 minus or not, okay, in a relation, it has exactly the same amount of information. Yeah, it's between psi A and QB tilde, but the anti-commutator, okay, so the relationship was, so basically in the process of passing, right, if you pick up any anti-commutator from C0 minus, that doesn't have any C00 mode, right? So once you apply B0 minus, okay, if you pick up any anti-commutator from C0 minus, right, that cannot protect you from getting annihilated by B0 minus. So, okay, so the relation is let me write this. So what you can do is you can write this as psi A C0 minus QB tilde B0 plus B0 minus equal to 0. Okay. And now the point is because B0 minus kills this, right, you have to make sure that there is somewhere a C0 minus in between which protects you from B0 minus passing through this and hitting the psi. Okay. So, and for that, what you can do is that you take QB tilde, okay, for example, QB while passing through C0 minus will pick up some anti-commutator terms, right, but that doesn't have a C0 minus. Okay. So that will get annihilated immediately because B0 minus will not kill it. Okay, so using that argument one can show that this implies that B0 plus QB hat psi A is equal to 0. So the general rule of thumb is that the C0 minus, okay, even though it doesn't commute with everything, okay, unlike B0 minus, okay, you can pretend as if it commutes or anti-commutes with everything because if it doesn't, okay, any anti-commutator of C0 minus, okay, will basically get annihilated once you apply B0 minus. Okay, so that's why you can pretend as if C0 minus just anti-commutes or commutes with the relevant operators. Okay, so you see from here that phi and psi satisfy various similar relations, right? Because these are just conjugates of each other, right? These are just conjugates of each other. Okay, so when you try to classify the kind of states that phi can be, okay, they are the same kind of states that psi can be. Okay, and that's not surprising because the propagator after all is symmetric. Okay, whether you are looking at the left side or the right side, it should give the same result. Okay, so now then we will try to look for basis of phi A. Okay. So I will be working at a specific value of m, okay, which means fix your m, capital M, okay, k square plus m square equal to 0. For that momentum, okay, we have this general classification that delta 0 has this form, delta 0 has this form. Okay. But now the question is, what are the possible choices for phi a? Okay. And I have already given some conditions that phi a has to satisfy. Okay. Subject to these conditions, can you classify what kind of basis states we should have? Okay. So we will classify the basis states of phi a in the following way. Okay. First, there will be unphysical states, which I will call okay. I'll give the names later. So unphysical states will be those okay, which satisfy that QB hat phi a is not equal to 0, okay, but B naught plus QB hat phi a is 0. See, phi a has to satisfy B naught plus QB hat phi a equal to 0. Okay, this is, I mean, you only classify states which satisfy this. Okay. But if phi a itself doesn't get annihilated by QB hat, okay, that we declare as unphysical. Then you have physical states. No, within H hat T, because phi and psi are already inside H hat T. Okay.
So we don't have to worry about the first two conditions.
About the?
About the first two conditions, that B naught plus and P x.
No, we have to, because B naught plus H hat T contains also states which are not annihilated by B naught plus. H hat T is annihilated by B naught minus, right? Yeah, so B naught minus annihilates it, but this is an extra condition. So let me write that. So B naught plus phi a should also be 0. Okay, these are automatic, these have to be the case. Okay, otherwise it's not a candidate for phi a. Okay. Now I am saying that let these be satisfied, but let QB hat phi a not be 0. That's what we will call unphysical state. Because it's not physical, it's not annihilated by QB hat, right? As we have seen, the physical states are the ones which are annihilated by QB hat. Right? These are not. So when these appear as external states, so if, for example, any of these states okay, start contributing in delta 0, then you are in trouble, right? Because that means the propagating state has these unphysical states propagating, right, which are not physical. Okay, so you have to ensure that these states cancel. Then you have physical states, which will classify as QB hat phi a equal to 0, okay, and B naught plus phi a equal to 0. Okay, then this is of course automatic because QB hat phi a is 0. Okay. But phi a is not of the form QB hat lambda a for B naught plus lambda a equal to 0. Okay. So this I put in quotes, okay, because normally when you define pure gauge states, you don't impose this condition, right? The B naught plus lambda a equal to 0 condition is not imposed normally. Okay, any state which is of the form QB hat lambda a, you declare as pure gauge, right? Because it's gauge transformation of something. But let's put this condition in, okay, it's just useful, okay, later on we can try to relax it. So in this definition, okay, the price we pay is the sum of the physical states are actually pure gauge, okay, because some of the physical states may be of the form QB hat lambda, sorry, this is QB hat, may be of the form QB hat lambda a for lambda a which are not annihilated by B naught plus. Okay, those we are counting here as physical, but those should be actually pure gauge. Okay, but let's just live with that. And then you have pure gauge. Where phi a is QB hat lambda a with B naught plus lambda A equal to 0. And of course B naught plus QB hat lambda equal to 0. Okay, so these phi a's also satisfy all of these conditions. Okay. Let me write these conditions here. This is condition A, and this is condition B. So you see that B naught plus QB hat phi A equal to 0 because QB hat square is 0. Right? So the condition A is automatically satisfied for states of that kind. Okay. And condition B is satisfied because B naught plus phi A is 0. But because I have demanded this. Okay. This condition ensures that B naught plus phi A equal to 0. Yes.
These conditions show B naught plus and QB hat.
Yes.
Can we think of them as conditions about L naught plus?
See, L naught plus is 0. See, L naught plus is always 0 for these states because these are the ones corresponding to poles. Okay, it's not actually L naught plus, it's a renormalized L naught plus, right? So it's not directly a condition on L naught plus, right? Because we are demanding that k square plus m square equal to 0, that to leading order that's L naught plus equal to 0, but then there are quantum corrections.
Okay, so L naught plus would be QB times B naught plus. QB committed.
Anti-commutative B naught plus, yeah. But this is QB hat.
This is QB hat hence.
So that's why it's a renormalized version of L naught plus.
There's some L hat not.
Exactly, yeah. Yeah, you can define,
So
yeah, in fact, whatever is in the denominator, right, is the analog of L naught, L hat naught plus, right? And that being 0 is the initial assumption that we are looking at the pole, right, so which means we are looking at k square plus m square equal to 0 for that value of k. So all of these states by definition automatically has that L hat naught plus equal to 0.
So for example, if you have a state
Yes.
annihilated both by B naught plus and also this renormalized L hat naught plus.
Yes.
It's an anti-commutator between QB hat and B naught plus.
That's right.
Then it is automatic that it is B naught plus QB hat is 0.
Exactly, yeah, that's right. So these are, so that means these are the ones, so B naught plus phi A equal to 0 is just the condition that it's a Siegel gauge propagator, right? Because that's the gauge condition you have chosen. So any state that propagates must satisfy B naught plus phi A equal to 0, right? And this condition that B naught plus QB hat equal to 0, right? The second condition,
It's really L hat naught.
yeah, is really L hat naught plus. It's basically the condition that this corresponds to the poles, right? Because we are interested in looking at the coefficients of the poles, the residue at the poles, right? So it's exactly the analog of the L hat naught plus, right? If you had done this in the field theory, right, without interactions, then this would be exactly the analog of L hat naught plus, L naught plus. Okay, so this will be the condition that L naught plus phi A equal to 0, and this will be the condition that B naught plus phi A equal to 0. So this is not renormalized because you are using Siegel gauge. That's forced by gauge condition, right? But this is renormalized, right, because there is mass renormalization.
So QB hat B naught plus.
Yes.
If it correct that, it will be like L hat naught plus. For example, if I just look at the 0 mode contribution, just the k square plus B normalized mass square.
QB hat commutator B naught plus. I think it's basically encoded in whatever this. Okay, I mean I have already put this equal to 0, so I have not put the actual m square because it's, see, L naught plus is not renormalized mass square, it's actually 0 because it's k square plus m square, right? So you have to somehow strip off the k square part, right? Yes, so if you subtract off the k square part, I think it is, by definition it's the m square because this is being done at k square plus m square equal to 0, right? So once you remove the k square part, it is minus m square.
It's a minus capital M square.
Minus capital M square, exactly. But in this analysis, or even in the free theory analysis, we don't normally strip off the k square part. It's all part of the same conformal field theory data. So L naught plus is not actually mass square, but it's just 0 by constant. That's where the poles are. Yeah.
Before going to the poles, you can just duplicate expression and it will be k square plus x square.
Exactly, yeah. So if you use a full delta f, right, then of course you haven't gone to the poles yet. There is a g sitting on the right hand side. Right? So that will have more information, right? Because you can now expand it around the pole, for example. You not only did have the leading part, but you also have the subleading contributions. Here by definition, you have already gone to L naught plus equal to 0 states, right? Yeah, L hat naught plus equal to 0 state, exactly. Okay, so now I'll choose a basis. Okay, so this is, here I have not chosen a basis yet, I just characterize the states in 3 different classes. Okay, so now this tells us that we can choose a basis of phi a in the following way. Okay, again I emphasize that this is expected to be a finite number of terms, finite dimensional space, but I'm not going to use it. So first I'll introduce UR. Okay, these are the unphysical states. Okay, so the URs are the ones which satisfy these relations. Okay, that they are not, the QB hat on UR is not equal to 0. Then I have PA, these are physical. Okay, so they satisfy that QB hat PA equal to 0, but PA itself is not equal to QB hat on something which that something is added by B naught plus. Yes.
In this definition of physical state,
Yes.
you said there are sometimes pure gauge states are also included, that is the lambda A's which do not satisfy B naught plus.
That's right, exactly.
So are these the gauge transformations which take you out of the single gauge?
That's right, yes. So these will be the gauge transformations which take you out of the single gauge. The gauge transform, well, they don't take you out of the single gauge. The gauge transformation parameter itself is not in the single gauge, right? Because lambda is here the gauge transformation parameter. So it may happen sometimes, right, that you gauge transformation parameter is not in the single gauge, but after you apply QB hat, you come back to single gauge. Okay? Those are the states which are counted as physical states. Right? But we will see eventually that they don't matter because they will decouple from the amplitude anyway. Okay, so you don't have to worry about this. So just classify them as physical for now. Okay, even though there may be accidentally some states of that kind. Okay, that you take a gauge transformation parameter outside single gauge, somehow after applying QB hat you come back to single gauge. Okay, so now the unphysical states, the pure gauge states. Okay, for pure gauge states, we don't have to introduce actually another index. Okay. We'll take the pure gauge states of the form QB hat UR. These are pure gauge. Okay, in fact, this is the only subtle point here. Okay, that all pure gauge states can be written already in the basis of unphysical states. Okay, because you see that what is the definition of pure gauge state? It should be writable as QB hat on something, that it is. Okay. And what does that something have to satisfy? Okay. It has to satisfy that B naught plus lambda equal to 0. So B naught plus UR should be 0. Okay, which is of course true because UR is an unphysical state which satisfies already that B naught plus on UR equal to 0. Okay. And it has to satisfy B naught plus QB hat on UR equal to 0, which of course it does because this is one of the conditions on the unphysical states. Okay. So this in fact looks trivial, but this will be the key point that in this basis, okay, physical states stand by themselves, okay, but the unphysical and the pure gauge states always come in pairs. Okay, given any unphysical state, you can construct a pure gauge state, of course not of the same Gauss number, it's Gauss number 1 hat. Okay. But nevertheless, for given any unphysical state, you can construct a pure gauge state by applying QB hat. Okay. And all pure gauge states come this way, okay, by applying QB hat on an unphysical state. Is this point clear? So let me repeat again. What I have done here is that I have a phi A, okay, which satisfies conditions A and B. Okay, these are the two conditions that it satisfies. And what I claim, okay, so let me write down the conditions maybe here. It will be clear. So B naught plus UR should be 0. Okay. QB hat B naught plus UR should be 0. UR is not equal to QB hat. Well, UR of course cannot be. It's fine. Yes, thank you. B naught plus QB hat UR equal to 0. Okay. Then QB hat PA equal to 0, and PA is not equal to QB hat lambda A with B naught plus lambda A equal to 0. Okay. No condition, no further condition, this is automatically. So given the UR and PA satisfying these conditions, this is the choice of basis. Okay. Phi A can be either UR or PA or QB hat UR, okay, or any linear combination of these. So now using this I will expand delta naught as PABA, okay, all repeated indices are summed over. Okay, because I have chosen these as the basis, right? I can always write as PA times some state, UR times some state, QB hat UR times some state. Okay. Now each of these, each of BA, CR and DR can be a linear combination of unphysical, physical and pure gauge states. Okay, because so far I have not done anything on the right hand side. I have just classified these. Okay, the classification on the right hand side of course is also the same because they satisfy the same conditions. Okay, but it's not that physical is paired with physical, this is paired with unphysical and this is paired with pure gauge, right? There is no reason to believe that that is the case. So in general, this can be any linear combination of the three classes of states, this can be any linear combination of three classes of states, and so can this be. Now this delta naught that I have written, okay, automatically satisfies condition 2 and condition 3 because that's the way the bases have been chosen. Okay, B naught plus delta naught. Why is it 0? Because B naught plus when it's applying on PA, right? By definition it annihilates all of these. Okay, and the same thing, these are of course chosen to satisfy those conditions. So condition 2 is implemented and condition 3 is also implemented, okay, because that's the way you have chosen the basis states. But condition 1 has not been implemented. Okay, this is something that will now give new conditions, okay, which will help us determine the B, C and D. Okay, or at least put some constraints on B, C and D. Okay, and I will see what structure we get. So now apply condition 1. So the first term, QB hat delta naught C naught minus. Okay. You see QB hat kills PA, right? Because physical states are added by QB hat by definition. It kills this term because QB hat square is 0. Okay. So the only term that it doesn't kill is this one. Okay. So you get QB hat UR times CR, C0 minus. And then I have to write the rest of the terms, delta naught C naught minus QB tilde. Okay. So there we have no choice, you have to write the whole thing. So BA C naught minus QB tilde plus UR CR C naught minus QB tilde plus QB hat UR so this will vanish. Right, from the condition 1. And now we will use the fact that these are linearly independent, right? This is the basis state. So QB hat UR, PA and UR are linearly independent basis states. Okay. So the coefficient of PA must vanish, coefficient of UR must vanish, and coefficient of QB hat UR must vanish, which means the sum of these two must vanish. Okay, so I think now I can erase this because I have already implemented the condition. So this gives a certain relation. So first let's look at this term. Okay. BA C0 minus QB tilde equal to 0. Okay, we can put a B0 minus here if you want. Okay. So this implies again by this conjugation property that QB hat BA must vanish. Okay, we just apply B0 minus, okay, so that QB hat now can be commuted through C0 minus and it just acts on BA. So this means that BA is a physical state, physical or pure gauge state. Now let's look at the QB hat UR coefficient. So you get CR plus, again I apply B0 minus, dr C0 minus QB tilde B0 minus equal to 0. Okay, and again by this property now I'll keep track of the sign. Okay. CR plus, okay, so QB tilde, okay, let me write expression first. Okay. So there are several signs that you have to worry about. So QB tilde, okay, has to come here, right? Okay. So in that process QB tilde passes through C0 minus and dr. Right? QB tilde has to pass to C0 minus and dr. So that gives you dr plus 1. Okay, what is minus 1 to the dr? Okay, so minus 1 to the, so dr in the exponent, dr in exponent is just the Grassmann parity of dr. Okay, this is the convention we are going to use, otherwise it just have to introduce another index. Okay, so when I say minus 1 to the dr, it's basically dr is 0 if it's Grassmann even, it's 1 if it's Grassmann odd. Okay, so QB tilde basically picks up one minus sign because it has to pass to C0 minus, but another factor of minus 1 to the dr because it has to pass to dr because it comes here. Okay, but there is one more minus sign which is has to do with the fact that the QB tilde, okay, instead of acting to the right, that's how you normally define it. Okay, now it's acting on the left. Okay, because it's acting on the dr. Okay, so when a dimension 1 current, okay, acts on the left instead of on the right, it picks up another minus sign. Okay, so there is another minus sign here, so it's actually this. Okay, these minus signs are not very important. Okay, eventually they all cancel. Okay, but it's good to keep track of them. So this basically tells us that CR must be equal to QB hat dr. Sorry, minus 1 to the power dr plus 1 times QB hat dr. So this is condition 2. Okay. And the final condition in fact is trivially satisfied. Okay. So that's the coefficient of UR. Okay, the coefficient of UR gives you CR C naught minus QB tilde, put a B naught minus again, is equal to 0. So this tells us that QB hat CR equal to 0. Okay. But QB hat CR of course is 0 by this, because QB hat CR is QB hat square dr. Okay, and QB hat square is 0. Okay, so this is trivial. So this was condition 3, but automatic. Okay, so using this, now I am going to write down the expression for delta naught. So this is the decomposition of the propagator or the pole residue at the pole of the propagator in terms of states. Okay. So there is a physical, okay, because BA is either physical or pure gauge, so let's declare all of those as physical. So there is a physical term, then there is an unphysical pure gauge term. Okay, QB hat dr by definition is pure gauge, and then there is a pure gauge times unphysical. Okay, in general dr is not annihilated by QB hat. So this is the general structure. Okay, but I have not said anything about BA, dr and how these are related to the basis states, so we will not say it till the very end. Is this clear? Okay. Now the point is that if these terms had not been there, then you are done. Okay? Because suppose you have a cut diagram. Okay, so let me now write this draw this here. We have gamma L and gamma R. Okay, we cut it. Let me draw the cut by some red line. Okay. These are all physical states. Okay. These are annihilated by QB hat. By QB hat. Okay. Similarly, these are all annihilated by QB hat. Okay. Here, we have to insert for each of these propagators, you have this decomposition. Okay. Now, if these were not there, okay, then each of these states are either physical or pure gauge, right? Because PA, as we have said, that we have called that physical in quotes, but some of those could be pure gauge because it may have the form QB hat on something which is not satisfying the single gauge condition. Okay. But anything that is pure gauge will now decouple because of this identity. If you remember, okay, gamma of or sum over I equal to 1 to n, gamma A1 up to QB hat AI n, this is equal to 0. Okay. So this implies that if all of them are physical except one, which is QB hat on something, that amplitude is identically 0. Okay, because everything else has QB hat on that equal to 0. So then this would mean, so if this was the only term, okay, that is there, then it's automatic that only physical states contribution, okay, survives on both sides, okay, and that will prove the Katkowski rules, the unitarity, okay, because then only physical states propagate, and then of course these are not normalized basis, right? I have never said that P and B are normalized, okay. So now if you re-express them in terms of the normalized states, okay, then you will pick up some wave function normalization factor, right, which goes into the LSD formalism. Okay. So this is the goal, that we have to show that from each of these terms only this part contributes. Okay, the others go away. Well, you are not completely done. We'll see that there are some subtleties still, right, which you have to manage, right? For some simple terms, you are already done, right? So we'll now describe the simple terms and then one example of a more complicated term. Okay, we'll see where the complication comes from. Okay. If we are already done at a very trivial level, then you see we don't see the fact that we have to, that the loops of matter cancel to the loops of ghosts, right? We know that something like that has to happen, right? It cannot be that term by term it's 0, right? Because in gauge theory, for example, we know that the loops of matter, the extra matter actually cancel the loops of ghosts, right? And we will see how that comes about in this language, in this formalism. So what we have in the insertion is product over I equal to 1 to n delta naught I okay, where delta naught I corresponds to the delta naught for the ith propagator. Okay, the n is the total number, this is 1, 2 up to n. Okay, n is the total number of states that's in the, well, this n is not the same as this n. Okay, so let's call this some m. So let's write it out. Okay. And as I have already said, the desired term is product over I equal to 1 to n PAI. PAI. Okay, this is one of the terms. So let's start with the simplest non-desired term. Okay. The simplest non-desired term will be the one where n minus 1 of these factors are of this kind, okay, and one factor is of the rest kind. Okay, that's clearly the simplest. So the simplest non-desired term is product, well, let me write the first one first. So minus 1 to the power dr 1. Okay, so the fact that I am taking the first one of the undesired kind is totally immaterial. I could have taken any of them. This one is easy to see that it vanishes because of the following reason. Okay. So let's look at the first term. Okay, let's pick this one. In this one, okay, let's look at what are the states being inserted on gamma r. Okay. So gamma r for this one, the gamma r, okay, has in its argument, one is of course this one. This is being inserted on the right. Okay. So QB hat D1R. Okay. Then we have the set of states which are BIA. For I greater than or equal to 2. Okay. And we have external states. Okay, that's the structure of gamma r, right? One of the states, this one gave QB hat D1R. Okay, these are all physical because B's are physical, or B's are annotated by QB hat, okay, and these are of course physical. But this is 0 because this has one QB hat on something and the rest are all physical or annotated by QB hat. Okay, so by this identity that you have here, okay, this is identically 0. Is this clear? Okay. Similarly, this term, okay, vanishes because gamma L vanishes because gamma L now has QB hat U1R then the set of PIA for I greater than or equal to 2 and external states, and this is 0. Okay. So because each term is a product of gamma L and gamma R, okay, if you pick the first factor, then the gamma R makes it vanish. If you pick the second factor, then gamma L makes it vanish. Okay, so you are done. The simplest non-desired term doesn't bother us. Okay, that is 0 anyway. So now I do the next simplest non-desired term, and this is in fact a prototype typical of the general case. Okay, so once I do this, I then the rest should be obvious how to proceed. So here I pick two factors of this kind, okay, and the rest of this kind. Now you see that if we pick, for example, so there are 4 terms now, right? You have to consider this times this times this, or this times this times this, or this times this times this, or these 2 times this. 2 of them are 0 by the same kind of identity. So let me call these terms 1 and 2. Okay. So we have 1 times 1 plus 1 times 2 plus 2 times 1 plus 2 times 2. Okay. So of these, the claim is that these are 0 identically. Okay. So let's look at 1 times 1. Okay, that means I pick this and this. Okay. So here let's look at what are the arguments of gamma r. Okay. So the first argument is QB hat D1R, QB hat D1R, then QB hat D2R, then the set of BAI for I greater than or equal to 2 and external. This of course is 0. Okay, because this is up to a sign, QB hat acts on this which is 0 because QB hat square is 0, QB hat acts on these which are all 0 and QB hat acts on external which are all 0. Okay, so this is 0, no problem. Okay. Similarly 2 times 2 will vanish because of gamma L. Okay. Because on gamma L the insertions will be now QB hat U1R, QB hat U2R, PAI, sorry, PIA. So this is also 0. So the problematic terms are these 2, this and this. Okay, let's say why. Okay, so let's look at 1 times 2. 1 times 2. Okay. So we have to work out both gamma L and gamma R and see if any of them vanish. Okay. So in gamma L, the insertions are U1R, QB hat U2R, okay, and then the P's. And in gamma R, the insertions are 1 times 2, so QB hat D1R, D2R. But we see this doesn't vanish by itself, because on gamma L, there is a QB hat, okay, but there is also an unphysical state. Okay? So you cannot just move the key. So QB hat you can distribute, okay, you can strip it off from here and put it on the other states. These are all 0, okay, but you can put QB hat on this term and that doesn't vanish. Similarly, here there is a QB hat, okay, but there is also a D2 which doesn't get annihilated by QB hat necessarily. So that's also not 0. Okay, so neither gamma L nor gamma R vanishes. Let's look at 2 times 1. 2 times 1 is this times this. So let's look at the gamma L first. And times gamma R. So gamma R, you see, it's 2 times 1, so D1R, and then QB had D2R, and then the B's. So this also doesn't vanish, right? Because while there is a QB hat, there is also an unphysical state. Okay? While there is a QB hat, there is also an unphysical state. But now you see that we can do something. Okay, so let's take this term over here. Okay, there is a QB hat here. Okay, it doesn't vanish, but by using this same word identity that is there, okay, we can move this QB hat on this at the cost of picking up some signs, right? Because it's a sum of many terms which is 0, okay? All the other terms are 0 by itself because QB hat acting on any of these gives 0, but you can just move QB hat from there to here. Is this clear? Similarly, in this term, okay, in gamma L, you can move QB hat from here to here. Okay. Now, you could have moved it in various different ways. I am doing this here because this is the general procedure that you always pick one of them which you declare as first entry, okay, and you move the QB hat in the first entry, from first entry to rest. Okay, that's what works for the general procedure. So suppose you do that. Then we see that these two terms are identical, right? Gamma L, U1, QB hat U2, okay, U1, QB hat U2, rest are the same. Similarly in gamma R, here you have D1, QB hat D2, d1 qb hat d2. Rest are the same. Okay. So you now have two identical terms. Okay, you have to do a little more work to fix the signs. Okay, and so for fixing the signs, it's best to do it just at this level. Okay, at this level, what you are doing here is that you are moving this qb hat from there to here, and in the second term, you are moving the qb hat, okay, from here to here. Okay, you always move in the first entry. Okay, so you can work out what the sign would be. Okay, it just requires a little effort to do this. Okay, sorry, so in the 1, 2, you move it here. Okay, in 2, 1, you move it here. Okay, always in the first entry. Okay, and in that process, because qb hat is Grassmann odd and you have these have some Grassmann parities, you will pick up some signs. Okay, but at the end of the day, we can show that these two terms are equal, but up to a sign. Okay, there is a minus sign in between the two terms, and that's what makes this cancel. Okay, and the cancellation you can see works between states whose ghost numbers, the propagating states whose ghost numbers differ by 1. Okay, because to initially, okay, the amplitudes that you have, we have an u1 are inserted here. Okay, but here you have a qb hat u1 are inserted, which has ghost number 1 higher. Okay, so if this is matter, this is ghost. Okay, so the cancellation always takes between two different sets of states of different ghost numbers. Okay, and that's the hallmark of what happens in gauge theory, that the ghosts cancel the matter contribution. Okay, you always, and in this case it's of course more general, right? Because there can be ghosts at various levels. Okay, there are infinite set of ghosts. Okay, so the cancellation is always between a given ghost number sector and a sector which has ghost number 1 less or 1 higher. Okay, so now let me just state what happens in the general case. Okay, you can work out the sign, I will not do that. Okay, it's just a little involved. Okay. So general strategy. Okay, so general case will have the following structure. So suppose there are k terms of this kind, okay, and then from k plus 1 to n, it's PIA. Okay. So what you do is that you expand this out. Okay, there are 2 to the k terms now. Okay, because from each of this k you can either pick the first one or the second one. Okay. But in each of the 2 to the k, okay, you focus on the first entry, which means the one that comes from the I equal to 1 term. Okay. So the I equal to 1 term, okay, either has minus of minus 1 to the power dr1, ur1, qb hat dr1, or it has the second one, qb hat ur1 dr1. Okay, it has one of these terms. If it has this term, okay, this is inserted on gamma r, okay, you move this qb hat from here to the rest of the states. Okay, rest of the states which are unphysical. Okay, if some of the states, see, rest of the states will be what? They are external states, which of course are physical. Okay, they are inherited by qb hat. Okay. Then there are some entries which are qb hat d. Okay, they are also annihilated. There are some entries which are B, which are also annihilated by QB hat. Okay? But there are some entries which are just D, DRI. Okay? Those contribute because QB hat now moves into those DRIs. Okay, so you keep those terms. Similarly, whenever you have this term, okay, you take this QB hat, which is again on the first entry, the UR1, and you move it to the rest. Okay, expresses the sum of terms. Okay, and so this QB hat will act on the other URIs, okay, which are inserted in the amplitude. Okay, the rest doesn't matter. Okay. And then what we can show is that the set of terms that we generate this way, moving this one, okay, or moving this one. Okay, so this one is moved on gamma L, this one is moved on gamma R. Okay. The set of terms that we generate are in one-to-one correspondence. Each term is paired. Okay, for every term in one set, okay, that you obtain from here, there is a term in the other set that you obtain from here. Okay. So the terms are paired, and furthermore you can show that they always come with opposite sign. Okay. So all these terms cancel pairwise, okay, which is again a reflection of the fact that the matter and ghost are states of different ghost numbers propagating in the loop are cancelling. Okay. So this is the way we show that all the terms that are unwanted actually cancel, and what you are left with is the only term where each term is of the form P times B. Okay, and that of course is a physical state, and then you can normalize by expressing in terms of the standard basis, some normalized basis, and that gives the wave function normalization. Right? That's the residue at the pole. So that's the way you establish the unitarity of the theory. Okay, the perturbative unitarity. Okay, I think that's about it. I'll stop. Yeah, I think this proof, okay, I have not thought very much about it, but it's in principle possible to extend this proof. I mean, think of this also as a proof in usual gauge theories. The point is you have to rewrite a gauge theory in a way where the kinetic term has this form of psi QB psi. See, that was critical here, right? The kinetic term, after you have gauge fixed, it has a form psi QB, C naught minus QB hat psi. But that should be possible in usual gauge theory by possibly adding some auxiliary fields, because after all, string theory contains Yang-Mills theory as its low energy limit. Right? So it contains Yang-Mills theory, but it gets the Yang-Mills theory in terms of also some auxiliary fields. Right? So maybe what one has to do is to rewrite the usual Yang-Mills theory by adding auxiliary fields of the kind which allows you to write the action as psi q psi, and then you should be able to extend it to usual Yang-Mills theory. That's right, yeah. But that should be automatic. I mean, it's after all gauge invariant, right? So one can do a BV quantization. Okay? It's just that even if you do the BV quantization of the usual Yang-Mills, the kinetic term may not have this form of psi q psi. Right? But that can be achieved by adding enough number of auxiliary fields. Right? Because here we can start with the string theory and go to the low energy limit and see how the Yang-Mills theory emerges, right? How the Maxwell-Lagrangian emerges, for example. And the way it appears is that you not only get the gauge fields, but also some auxiliary fields. Right? So it's a rewriting of the Yang-Mills theory with some additional fields.
What we get it would be to look at the world line formalism.
That's true, yeah.
So there, I think the QB psi equal to 0, you can get the equation.
Okay, yeah.
At least in Jim Gordon, we know that it works that way, because QB gives some C goes times C.
That is true, yeah, yeah.
Hamiltonian constraint is the correct.
That's true, yeah.
It's also true for the Dirac-Fabian, that
yeah, exactly, yeah.
single gauge in QB equal to 0 gives you the Dirac equation, which may be a thing about Yang-Mills equation.
That's true, yeah, yeah.
With the world line
That's true, yeah. Yeah, so I feel that, so this proof is general enough, so it should be extendable, right? As long as you can write it as psi q psi, there is no reason why it shouldn't be extendable to ordinary Yang-Mills.